This is our pre-calculus first 6 weeks final. This is a review of our test we had earlier this week. 17 problems total. And the first problem we have here, number one, which of the following functions is bounded? And I did do a little favor by putting above and below. So really the only candidate for that is going to be this one right here. Answer choice B. And to find that, if we go to the trig button in our calculator, we go to sign, and then we put X, and we see the oscillating function, and there is an upper boundary of 1 and a lower boundary of -1. Therefore, answer choice B is our correct answer for problem 1. Problem 2, for the following function, find the approximate interval over which it is decreasing. And again, we go to our calculator. What I did is I pre-entered a lot of these functions here, and this is the one entered for problem number 2. So we have this entered, we press enter, and where the function is decreasing, we say where, it means during what x values is the value of the function decreasing. And we have an x value here at about -1, decreasing from this relative maximum at x equals -1 toward the relative minimum. We can go ahead and trace if we want to. I guess that might be the easiest way to do that. We go to menu, trace, graph trace. If I come up to the left, we see here at the bottom right of the view screen, -1, 2.6. So that starts, there's a maximum at x equals -1. And then if we scroll to the right, we can get down to move below there, and we see minimum, and that's at x equals 5, and that's a minimum of -8.2. So from x equals 1 to x equals -1 rather to x equals 5, that is going to be our approximate value, approximate interval. I think that's actually an actual interval over which the function value is decreasing. Problem 3, which of the following functions has a vertical asymptote? Well, all these other functions, like if you have function in part A, that's going to be the square root function, not a vertical asymptote. Problem B, well, we already had one similar to problem B. That's going to be this sine function, no vertical asymptote. Answer choice D is going to be the parent quadratic function, no vertical asymptote. It's only this one, 1 over x plus 2. Do that. Go to Control I, add graph, 1 over x plus 2. There we have a vertical asymptote at x equals -2. So our answer choice for this is C. Next problem, number 4. This is one that gave a lot of my even better students a tough time. What I did is I pre-graphed or pre-entered a couple of these functions. One of the wrong answers and then a right answer. One of the wrong answers is B. And if we go to the calculator, Control I, add graph. I'm going to go up and get that. Okay, there it is. This is a wrong answer. We press that, and we see that we have an asymptote here. And if we investigate further, if we go to control T, so you get the table view, we see that that vertical asymptote is at x equals -5. So that kind of checks out. So a vertical asymptote is an evidence of a non-removable discontinuity. We want a removable discontinuity. And for that, we are going to go to the correct answer, which is A. See what that looks like. And here is answer choice A. You press that, get a line. No break. And so the no break is, if there is a discontinuity, is evidence of a removable discontinuity. And where do we see that discontinuity? Not graphed. We can't see a point discontinuity, hole, which is synonymous with hole, which is synonymous with removable discontinuity when graphed in a calculator. If we go to control T, we are going to see that x equals I thought it was a -5. It's actually going to be 5 at x equals 5. So there's a hole. If we go to x equals 5, we can't see it on this graph. There's a little hole up there at x equals 5. And last, I want to demonstrate algebraically how we can algebraically remove. We've already determined that A is the correct answer. Okay, we have x minus 5 in the denominator, and in the numerator we can write this numerator of x squared plus x minus 30 as quantity x minus 5 times quantity x plus 6. And we can algebraically remove this x minus 5 over x minus 5, leaving us with this x plus 6. So there still is a discontinuity at x equals 5, but we do not see it when graphed because it is a removable discontinuity. We algebraically removed it. So for all intents and purposes, this thing looks like the graph of the function f of x equals x plus 6. Next, problem 5. Which following functions has as a vertical asymptote the line x equals 5? Well, the temptation might be to look at answer choice C, 1 over x plus 5, and I will do that now. I'll put in 1 over x plus 5. And we see a vertical asymptote not at x equals 5, but rather as x equals -5. If we go to tab here, and I go to change this to minus 5, x minus 5 here in the denominator, we see a vertical asymptote at x equals 5. And algebraically, we could write that as, we would say that x minus 5, our denominator of answer choice B, cannot equal to 0. And if we solve for x, this inequality, by adding 5 to each side of the inequality, we would see that x cannot equal 5, which happens to be where our vertical asymptote is located. So our answer choice here is B. Next problem. 6. Compare the function y equals 3x minus 6, which is its inverse function. Well, we have step 1 is to change f of x to y. We already have that. So I'm going to change this y equals 3x minus 6 to x equals 3y minus 6. And if we add 6 to both sides of the equation, we get 3y equals x plus 6. And now if we divide both sides of this equation by 3, which means all terms on each side of the equation by 3, we have y equals 1/3 x plus 6 over 3, which is 2. So our correct answer is B. We could likewise graph these functions in a calculator, and if we graph them, we get this thing. Y equals 3x minus 6. Well, that's going to be 2, 3, 4, 5, 6. We're going to have a slope of 3, y-intercept of 6, so it's going to look something like this. And then our answer choice B is our inverse, and that's going to be the function y equals 1/3 x plus 2. So here we go to plus 2. And 1/3 x, so it's going to be the slope of 1/3, kind of like this. And these functions reflect about this line, y equals x, that I'm drawing in black now. See that? That's the y equals x. And these two inverses of each other, one mentioned up here, and answer choice B, reflect about each other, the line y equals x. Next, 7. What's the domain and interval notation of the function shown below? We can work this out algebraically. We know that 7 minus x inside the radical cannot be negative. So these have to be greater than or equal to 0. And so if we subtract x from both sides of this inequality, we get negative x is greater than or equal to negative 7. And if we multiply both sides of this equation by negative 1, we get x and then 7 on the other side, but we have to change the direction of the inequality so x is less than or equal to 7. I think that's going to correspond to answer choice A. It's not answer choice B because the bracket, and also graphing this function, which I have done. Go up to see it graphed here. There it is. Press enter. You see this function starting, going all the way from negative infinity up to and including x equals 7. We can tell that 7 is part of the domain because if we press Control T, we will see at x equals 7, the function is defined and equals 0, but greater than 7, error, this pound E error. So let's go on to the next problem, 8. What is the domain and interval notation of the function shown below? Well, for this, I have this one graphed also. And I'm going to graph Control I. This TI Inspire CX calculator is a very fine calculator. And here it is. We press that, we see a vertical asymptote at x equals 2. And accordingly, if we go to our answer, we would see any place that does not include 2 as a break. For instance, answer choice B or answer choice C, we can just cross out. So the only thing is, do we have another discontinuity besides at x equals 2? Well, if we go back to the calculator and we go to our table view, Control T, we will see that at x equals 0, we also have a discontinuity where it says undefined here at x equals 0. Therefore, we have a break in this function at x equals 2 and at x equals 0. The only place that is the case is right here. Another thing we can do algebraically, set our denominator to not equal to 0 and solve. Well, our common factor here between x squared and negative 2x is x. So x times x minus 2 is not equal to 0. So we know that x cannot equal 0, and x minus 2 cannot equal 0. So x cannot equal 2, which we already found out. So we set one factor not equal 0. The other factor, this one here, x minus 2 not equal to 0. Next problem, 9. Which of the following functions has a range of greater than or equal to -1, less than or equal to 1? That is going to be definitely answer choice B, which is our cosine function. Our cosine function, when graphed, is going to look like this. It's going to have a, it's going to go like this. And will oscillate between lower boundary of -1 down here and an upper boundary of 1 up here. So definitely that's going to be our range of this function. Answer choice B. Next, problem 10. Now this one really was almost embarrassingly easy. Now we have 3 sets of ordered pairs, which following which sets of ordered pairs represent the inverse of this relation. Well, we have 1, 2 up here. So one of our, to have this point as an inverse, is going to be 2, 1, which here in answer choice D. Likewise, we have 2, 4. Well, inverse of that point will be 4, 2. And the last point, 4, 9. Its inverse will be 9, 4. Our answer choice is D. Next, problem 11. Which of the following rational functions has no discontinuities? And I'm going to show you only one of them has no discontinuities. And in fact, all of these, the 3 wrong answers have vertical asymptotes. I think, well, anyway, I'm going to go ahead and look at answer choice A here, which is not a right answer. Control I. And go up here. There's answer choice I. We can see a vertical asymptote at x equals 2. So that is not a right answer. I want to show you the correct answer, which is B. And let's go up to that. Correct answer. It has no discontinuities. This appears not to have discontinuities, but just be certain, if we could go to Control T, we are most likely going to see a UN or UND. And it looks like the most suspect point here is at x equals 0. Well, x equals 0, at x equals 0, our output value is 5, and there is no discontinuity there. So our correct answer is B. One thing, to have a discontinuity, we have to have our denominator equal to 0. And if we set this x squared plus 1 not equal to 0, and we try to solve for x, we solve for x here, we get x squared is not equal to -1. Well, there's no way that there's no value of x that can equal -1, because we can't, if we take the square root, right, both sides of this, well, we have x equals or not equals plus or minus square root of -1. Well, that's going to be an imaginary number, so there's not a real number answer for that. There's no way this value of x squared can never be negative. And in order for there to be discontinuity, x squared would have to be negative, have to cancel out this positive 1 here. Next, problem 12, if f of x equals 2x minus 3 and g of x equals x plus 2, find f of g of x, and we see this composition function notation. So for f of g, we're taking the g function, which is next to the x, and plugging it in everywhere we see x in the f function. So we would say f of g of x is equal to 2, and I leave this parentheses here for the x minus 3. So inside this parentheses, I place x plus 1. And distributing, we have 2x plus 2 minus 3. And simplifying, we're going to have 2x, and 2 minus 3 is going to be minus 1. So our correct answer is going to be A. Next, 13. Which function is the inverse of the function f of x equals x cubed plus 1? We have the step process. We've demonstrated a lot here lately. So we change that f of x to y. So we have y equals x cubed plus 1. Next, we're going to switch the x and the y. So x is going to equal to y cubed plus 1. And next, I'm just going to rewrite this, kind of flip these around. Y cubed plus 1 equals x. And now to solve for y, which is what we're doing now, we're going to subtract out 1 from both sides of this equation. 1 minus 1 cancel. We have y cubed is equal to x minus 1. And if we take the cube root of y cubed, that's going to get y isolated. So we have y is equal to cube root of quantity x minus 1. And to rewrite this finally in inverse function notation, we would say f negative 1 of x equals cube root of x plus 1, and our, oops, minus 1. Changed signs there, didn't I? Okay. X minus 1. There we go. So our correct answer is A. Next, 14. For the graph of the function pictured below, what are the approximate coordinates of one of the local maxima? Well, local maximum means relative high point or relative maximum. There are two of them there, and I heard there's this one on the left, but there's also the one on the right. And I think a lot of people were kind of stuck on this one on the left, since obviously that one is higher. So you look for the coordinates here. We get negative 1, negative 2, negative 3, negative 4. So about negative 5 comma 3. Yeah, that's going to be the approximate coordinates to the one on the left, but that's none of the answer choices. The correct answer choice is going to be this one right here, which is over 7 to the right and up 2. And so that's going to be it right here, and that answer choice is B. Next, 15, the free response problems. We have, if I promised you you're going to have one like this, if f of x equals x plus 1 over x, and g of x equals x, what is f of g of 2? Well, first of all, we have to find g of 2. So for g of 2, it's going to be equal to, we're going to take that x and replace it with 2, because x, g of x equals x. So that's going to be 2. So we take this 2 we found here and plug it in right for this x here, and also for this x over here. So we would say f of g of x is going to be equal to 2 plus 1 over 2. And when you do this, you're going to get 5 over 2 as a fraction, or in decimalized form 2.5. So 2.5 is our answer. Up here we put 2.5 and bubble it in. So there's 2 and point, and down here 5. That's what this one should look like. Next free response problem, we have 16. The elevation in feet of a punted football is given by the function f of t equals 5 plus 74t minus 16t squared, where t is the number of seconds. The nearest tenth of a second, how long after being kicked does the football reach its maximum height? I had a couple people ask me the question, what's being asked for? It says, okay, this thing like how long, okay? And also to the nearest tenth of a second. Okay, what are we being asked for? Time. Okay, let's go to the calculator, and I saw people make different mistakes on this one. Um, one thing I saw people do was if you type in the function like I did here, okay, and you want to check what it is, okay, you graph it. Let's check the table view. So you take Control T, and we see, okay, well, it looks like the thing's reaching a maximum height maybe around x equals 2. So on the table, that's the highest value you see is 2. I had people answer 2 seconds. It would be 2 if this was symmetrical. If it's 63 feet high at 1 second and 63 feet high at 3 seconds, we would know at 2 seconds would be the maximum between those two, but they are not. So really, the way to do this in the calculator is to go up here, press enter, and you can just graph trace the thing. And so if you go to graph trace, and where are we? Okay, we just go, keep on going up. We're going to reach a maximum. Okay, reach this maximum, and it says maximum there at the top. You see that? And it says 2.31, 90.6. I had some people answer 90.6. And to the nearest tenth, that's another issue. Guys, when you have 2.31, what is the nearest tenth? Well, to the tenth is going to be 2.3. Now, if you happen to answer 2.31, which you shouldn't have, by the margin of error scoring, you still would get that right. But you just didn't follow directions if you put 2.31 or 2. So just bubbled in. This is what they would look like. Shouldn't get this wrong, but you got to look at it. They're going to ask for either the height or the amount of time. Here, we're asking for time. Okay, next, last one. The rational function g of x equals x over x times 21 plus x squared contains how many discontinuities? Mark your answer in the grid provided. Again, if you're just not careful about this, I had a lot of people who answered 2 because they assumed one discontinuity for x equals 0 and another one with this 1 plus x squared. Not the case. There is not a discontinuity for this factor 1 plus x squared. There's no way that 1 plus x squared can equal 0 because x squared can never be negative. For this 1 plus x squared equals 0, this x squared would have to be negative. That's impossible with real numbers. But really, a way to do this, if you go to Control I, again, I pre-entered this function, and here it is. We enter that, we see no discontinuities, but when we go to Control T, we see at x equals 0, undefined, and nowhere else. Now this wouldn't, if there were some removable discontinuity not right at the number, at the integer level, that could trick you or something like this, but there's only one discontinuity here. And accordingly, our answer choice for this is going to be 1. So if we just fill in 1, and just bubble that in, that would be our correct answer. And you can put 1 anywhere in this grid. Anyway, that's all 17 of the problems. I hope this has been helpful to you. I hope that the study of this can help you in your future endeavors in this class and others. Thanks for viewing.